So today we are supposed to start with chapter number 3, atomic structure. Now, it's understandable that the elements that we usually discuss in the periodic table, such as copper, if we cut them out into small pieces, the smallest or the basic or the fundamental particle would be atom. So atom is the smallest piece of element that can show all the properties of that element. It can be known as the smallest piece. If you can you split the atom further? Yes, you can. And usually we come up with three most basic particles: electrons, protons, and neutrons. But atom is the smallest piece of that specific element that can show all of its properties, either physical or chemical. Now, atoms can be joined together to make molecules. A molecule consists of two or more atoms that are chemically bonded. We'll get to bonding. We'll discuss what ionic, covalent, or metallic bonding is. For now, it is joined by covalent bonds. The simplest examples that we can come up with is hydrogen and water. Hydrogen consists of two atoms of hydrogen. It's a hydrogen molecule. When two atoms combine, we call it a molecule. Water is also a molecule because there are three atoms in total, two of hydrogen and one of oxygen, as shown over here. So this concept is pretty easy. Let's get to what we know or what can be a little bit puzzling in the exams. Now, what are atoms made up of? Atoms are made up of subatomic particles. We have discovered more than 100 subatomic particles, but we only discussed 3: protons, neutrons, and electrons at this level, because they are the fundamental particles. By using the word fundamental, what I'm trying to say is that every atom would contain these subatomic particles. Apart from that, whatever the rest are, they sometimes are present in one atom, may not be present in the other one. Considering these, neutrons are present in the innermost part, what we call the nucleus of an atom, as well as the protons. That's why they are in common known as nucleons, and nucleons mean anything that resides inside the nucleus. However, electrons are found at large distances compared to the size of nucleus. They are at present away from the nucleus, and they actually keep revolving around the nucleus. So let's just move forward. I think the idea is pretty easy. In order to explain them, what we do is that we go with a relative system of explanation. As protons, neutrons, and electrons are extremely small particles, so instead of going with their actual masses or actual charges, what we do is that we go with relative masses or relative charges. Now, the word relatives makes it very easy for us. Proton and neutron have almost the same mass, not exactly, almost the same mass, so we give them the easiest of values, 1. Electron, however, is very small particle as compared to proton or neutron, so the value is given as 1/1836. Now, this is in comparison to proton, and this value is even smaller. As you can see over here, 1/1836 is actually 0.0005, so the value becomes very small. So whenever we are going to consider masses of atoms, we can simply neglect electrons, because they are the lowest of masses in all of this table. When we talk about charge, the charge on neutron is 0. Actually, there is a better word to say it whenever you're writing. It's actually considered as neutron. The charge on proton and electron is equal. So what we write for them is 1. However, the charges on protons and electrons are actually opposite to one another. So we use symbols to represent them: plus for proton and negative for electron. These symbols are just to keep the difference that their charges oppose one another. Remember, the masses and charges are measured relative to one another because the actual values are incredibly small. As you can see, this many of protons weigh to 1 gram. So instead of writing this many zeros every time or coming up with this big numbers every time, what we do is that we go with relative scale, and it's very easy to work with relative scale because it simply is 1. Instead of writing the exponential form or the writing the huge numbers of 0 is considered difficult. I think that is self-explanatory. But if you have a question, go ahead.
No, that makes sense. I'm taking notes.
All right, good. Let's move on. Atomic number and mass number. Now, we identify humans on some specific features of humans which differentiate one human from another. I know on daily basis life, we can recognize humans by their faces or by how they sound, but actually, when it comes to recognizing humans in specific or by law, what we use are fingerprints, because fingerprints of humans are extremely difficult to match. Means one human would have a fingerprint which is different from the rest of the 6 billion on the planet. So that's how we identify them. When it comes to elements or atoms, the two numbers we come up with simple numbers to identify them are atomic number and mass number. They're actually the identifications of an atom. What are them? Atomic number is simply the number of protons in an atom. Any atom on the planet can be differentiated or identified by the number of protons present in it. Each of the 118 different elements have different numbers of protons. For example, if an atom has 8 protons, it must be an oxygen atom. Atomic number is equal to number of protons. It's as simple as that. So just like human fingerprints, this is the way we identify atoms. All right. So whenever you are going to experience the atomic numbers in the periodic table, try keeping them in mind for a faster working. We say that for the first 20 elements, it's better if you remember the atomic numbers and the masses of the first 20 elements. That means we're talking about from hydrogen all the way to calcium. Your working will be much faster if you remember that. If you don't, it's not that you won't have the periodic table with you in the paper. Of course, that's a part of the paper and you will have it. But every time referring to the page back and forth takes a lot of time in exams. So it's better, and we always suggest our students to keep the first 20 elements, the atomic numbers and mass numbers in mind. You don't need to cram them. Actually, the frequent usage would make sure that you automatically memorize them. Moving on to the next identification number, that is mass number. Now, as the name suggests, it is also the nucleon number. The word nucleon is something I explained earlier in order to make this one easier for you. Now, if you remember, I said that nucleon are actually something that resides inside the nucleus. Now, there were only 2 subatomic particles that resided inside the nucleus. One was proton, second one was neutron. Electrons were not residing inside the nucleus. Instead, they were revolving around it. So it's pretty easy. Mass number or nucleon number is number of protons plus number of neutrons, anything residing inside the nucleus. So we add them up. Now here, they haven't given any kind of symbols. Let's see if they have symbols on the next page. If they do, good enough. If they don't, I'll explain what the symbols. There you go. There they are. For example, an element is represented by its symbol. Then the atomic number will also always be written on its left bottom, and the mass number would be written at left top. This is the superscript, this is the subscript, this is the atomic number, this is the mass number. This one is just the number of protons, this one is the number of protons plus neutrons. So it's very easy to work with. The number of neutrons would be mass number minus atomic number. Because this one already has protons, this one has protons and neutrons. Subtract these two numbers, you'll get number of protons, something which is a common question in IGCSE exams. And it's pretty easy to work with. 59 minus 27, 32 neutrons in cobalt. Which brings us to the question, are atoms of the same element different from one another? Yes, it can be. It is very much possible, and that's why we have the topic isotopes. Now, how can they be different? The example taken over here is pretty easy. This is a carbon atom. This one also is, and there are three different carbon atoms shown over here. Take a look, the number of protons in each atom is same. What's different are the number of neutrons. They're different in each atom. So we have 6 and 12, 6 and 13, and 6 and 14, giving us 6 neutrons, 7 neutrons, and 8 neutrons, respectively. We call them isotopes. As simple as it may seem, it is defined in the same way. They have the same number of protons, but they have different number of neutrons, and we call them isotopes. They are the atoms of same element, however, they are differentiated on the basis of different neutrons. So isotopes are the atoms of the same element which have the same atomic number but different mass number. They have same number of protons and electrons, but they have different number of neutrons. That's the exact definition of isotopes. Now, that the fact they have varying number of neutrons makes no difference to their chemical reactions. Noted down, this line is very important and has been considered in past papers as well. Chemical properties are actually controlled by the number and arrangement of electrons, which is actually identical for all three isotopes given over here. So the chemical properties of these three atoms, though they are different in the number of neutrons, we call them three different isotopes, but the chemical properties would be the same. What would be different? The physical properties can be different, especially the properties that are related to mass number. They can be different. Why? Because the masses of all three isotopes is different. Remember, this one is 12, so the isotope is written as carbon 12. This one is 13, the isotope is written as carbon 13. This one is 14, the isotope is written in as carbon 14. That's how you're supposed to write them in exams to mention a specific isotope. And that's how we call them. That's how we name them. Carbon 12, carbon 13, carbon 14. Now they will have different physical properties because their masses are different. Simply speaking, their number of neutrons are different. Clear enough?
Okay, so the actual definition of isotopes is that they're different atomic forms of the same element, which have same number of protons but different amount of neutrons.
Right, right. These three lines in the center is the exact definition that you are supposed to write in exams if they ask a question like this. Usually there is hardly one definition across the whole paper. There may be two at maximum. So you're supposed to write these three lines if it comes as a part of definition. As a part of understanding, they'll have different number of neutrons. They will have same chemical properties, but different physical properties. Okay.
What do you mean by different physical properties? What are like examples?
For example, the easiest of examples would be density. Now, density is actually depends upon mass over volume. The mass for these three atoms, these three isotopes is different. This one is the lightest isotope. This one is the heaviest. This one is the least dense isotope. Of course, this one is going to be the most dense isotope. This one is least dense, and this one is most dense. That's because of its mass. More the number of neutrons, heavier the isotope is going to be. Less the number of neutrons, lighter the isotope is going to be. So to start with, the physical properties such as mass, such as density, changes, or anything that depends upon mass is going to change, which includes, if you're going to ask more after density, you may quote the rate of diffusion, you may quote viscosity, because the rate of diffusion, as we studied earlier, also depended upon mass. We studied the very simple rule that lighter gases diffuse faster, however, heavier gases diffuse slower. So yeah, a property that depends upon mass would be different for different isotopes. Although carbon is not a gas, but if we consider gases such as chlorine has an isotope which is known as Cl35, and then there is another isotope of chlorine which is known as Cl37. Cl35 has a faster rate of diffusion as compared to Cl37. That's because Cl37 is heavier than Cl35. So of course it is going to diffuse slower. That's how you also interconnect the topics with one another. This is not given in the book, but as soon as you're going to face a few past papers, you understand how to interlink two different topics in the book because of having the linking or relative or interlinking content.
Okay. And about the chemical properties, the element having more neutrons than the original carbon won't affect any chemical reactions.
Chemical reactions are totally directed by the number of electrons or arrangement of electrons that's written over here.
Okay.
As the number and arrangement of electrons of all three isotopes is same. This one has 6 electrons in its shells. This one has 6. This one has 6. So there won't be any difference in chemical properties. All right, it's written right over
we
here.
can move on.
Good. Let's clear it up. Move on. Relative atomic mass. Now, this is something they have taken right off of the periodic table. This is chlorine. It's with a symbol. The atomic number is written below, and on top we have the relative atomic mass. We never wrote the mass number because if we write mass numbers on top, we'll have different isotopes and different elements have different isotopes. There are some elements which has only one isotope, for example, gold. And there are some elements which have like 16 isotopes or 18 isotopes or 10 or 8 different isotopes. So we can't go on and keep putting all the isotopes in the periodic table. So we have came up with a method of a relative atomic mass definition, and we'll tell you how we came up with this number 35.5. Okay. In order to connect both the ideas, let's take a look. 35.5 means that if you're going to subtract these two numbers and find out the number of neutrons, it's 18.5. It's not possible to half a neutron. So there must be something wrong with it. Actually, this is not the mass number of chlorine. This is the relative atomic mass, which is also shown by AR. Now, how do we come up with this? In order to explain that, there is something you must need to know. Chlorine consists of two isotopes, Cl35 and Cl37. A naturally occurring sample contains a mixture of these, and this mixture actually contains them in different abundance. Now, what we do is that relative atomic mass is the average mass of an atom, taken into account the amount of each isotope present in a naturally occurring sample of the element. All right, so if we go ahead and take a look, let me define it. If we talk about chlorine, there is one sample that has 35 mass number. There is another that has 37. Now, this one is 75% abundant in nature, like the naturally occurring sample he's talking about. And then this one is 25% abundant in nature. So we calculate them on the basis of their isotopic abundances, and we work with a weighted average. How do we find a weighted average is something also given over here in the example below. But let's work with this example so that this example is easier for you. Now consider 100 atoms in a natural sample. Of course, in 100 atoms, there would be 75 atoms of Cl35, and there will be 25 atoms of Cl37, right? Because if we are going to go with 100%, 75% of this occurs naturally, and this one as 25%. So we have a formula. In order to find AR, what we do is that we take the mass number and we multiply it by the relative abundance, which is 75%. This we do with the first isotope. We add it up to the second isotope that has the mass number of 37, and the relative abundance of 25. And we keep on doing that with different isotopes. After we are done adding all the isotopes, as this is an average, and average means to divide the number of particles you have taken, and we took or we considered 100 atoms to start with, the answer is supposed to be 35.5. This is how the weighted average is calculated, right? And the same thing would be given over here in example 1. In somewhat different words, maybe a couple of steps are different, but that's how we calculate the weighted average. So the weighted average talks about the mass number of all the isotopes, and there are natural occurring sample and the abundance they have in that natural occurring sample. What we do is that we take the mass of an isotope, multiply with its relative abundance, we add it up to the isotope number 2, its mass and its abundance, then isotope number 3, its mass and its abundance. No matter how many isotopes are there, doesn't matter, add them all up, divide them by 100, because we considered 100 atoms. That's how we were able to remove this percentage sign and simply write 25 or 75 over here. So your answer would be air, relative atomic mass. Fair enough. If you still have any confusions, we can always go with this example to explain further.
No, I understand.
All right, then let me raise this up. Are you done taking notes?
Yeah, I'm done.
Okay, let's raise this up. For example, a naturally occurring sample of boron consists of 20% boron 10 and 80% boron 11. So let's take that 20 and multiply it by 10. Let's take that 80 and multiply it by 11. Add them up. Consider 100 atoms. Divide them by 100. You'll get the relative atomic mass of boron. That is 10.8. And that's how we work with it. All right. So it's pretty much the same thing. They might be going with a different set of words, but the steps are literally the same. Shall we move on?
Yeah.
Okay, let's talk about electrons then. Atoms are electrically neutral and they have no overall charge. Why? Because the protons are positive one charged and the electrons are negative one charged. And as number of electrons and number of protons are same, so atom is electrically neutral. For example, we were talking about carbon. Carbon has 6 protons and 6 electrons. Every proton has +1 charge, so this can be multiplied by 6. And every electron has -1 charge. This can also be multiplied by 6. The answer to first one is +6. For the nucleus, the answer to second one is -6, and that's outside the nucleus, right? If you go by a mathematical operation, this comes out to be 0, and 0 means electrically neutral. The atoms are electrically neutral because the overall charge on proton can cancel out the effect of overall charge in electrons. Hence,
So there are never any situations where electrons aren't equal to the amount of protons.
yeah, there will be situation, and that situation is named as ions.
Ions, yeah. Okay.
The imbalance of electron and protons are actually ions. Lesser the electrons than protons, positive ions. More the electrons than protons, negative ions. That's how we deal with that scenario. But for atoms, as we're talking about atoms here only, atoms are electrically neutral because every time when we talk about an atom, it's understood that number of electrons are going to be equal to number of protons. Hence, electrically neutral, right?
Yeah, okay.
Okay,
We can
let's
move on.
move on. The periodic table. Now, there is a lot that you need to know about periodic table. However, a few of the things. atoms are arranged in the periodic table in the order of increasing atomic number. All right. So we need to be careful whenever we are going with that. Remember, against each symbol, there are two numbers, as we discussed earlier. One of them is atomic number, one of them is mass number, and this is the easiest step given over here. Atomic number is always the smaller number. No matter which number is written at top or which number is written at bottom. Let's see, if it's written like this one is supposed to be the atomic number, the bigger number is supposed to be the mass number. All right. That's how we differentiate between them. Let's say on a different way, on a different book or page, if it's written like this, just a second. If it's written like this, don't worry. The criteria of British writing or American writing might be different from one another. No matter how many times they switch this number, remember the smaller number is the atomic number and the bigger number is the mass number. And that's what they have been trying to explain it over here in these lines of the paragraph, right?
Yeah.
There are a few more things that you need to be careful about. Number of protons in an atom is equal to atomic number. Number of electrons in an atom is equal to the number of protons, and number of neutrons in the atom is equal to mass number minus atomic number, just like we did earlier. So that's how you can calculate all three of these. So when we are talking about, let's say, carbon 6 and 12, right? Carbon 6 and 12, this 6 is the number of protons, and the number of protons is equal to the number of electrons. But in case of neutrons, it is the bigger number subtracting the smaller number, and that's how you get the number of neutrons. This is what these three lines mean. So 6 is the number of protons, 6 is the number of electrons, and by subtracting the smaller number from the bigger number, 6 comes out to be the number of neutrons. All right?
Yeah.
Right. Let's move on. Take this example of uranium. 92 is the number of protons. Of course, it is going to have the same number of electrons. And 238 minus 92 is equal to 146, given at the bottom of this line is the number of neutrons. Right? So there we go. I think this concludes your chapter.